Hello and welcome to our next installment in MI210, the Essentials of Population PK/PD Modeling and Simulation. Today's lecture topic is a continuation of the Chapter 1 topic on nonlinear regression, but today we're going to get to the case of extending maximum likelihood to the population framework. Before we begin with that topic, I wanted to take a few minutes to review the homework problem and actually to assign a second one as well. Recall that we were discussing maximum likelihood methods for nonlinear regression problems, and we had introduced our hypothetical drug development problem where in our single ascending dose phase 1 study of MI2005A, our hypothetical drug, we collected data on some of the tolerability endpoints, and one of those was the QT interval. So ECGs were taken serially over time, and we've got here calculated a delta QTC change from baseline, which is plotted in the current display versus concentration. This is plasma concentration of our new drug. You can see from this relationship here that there's definitely an increasing trend with the delta QTC versus concentration, and not so clear what the pattern and the variability might be, but it looks at least to be a monotonically increasing relationship. Could be approximated by a straight line potentially as a starting point. Well, I'd like you to take this data set, and it's found in a file dqtc.csv, which is available on the course content site. And then to implement this in a naive pooled analysis, where you're going to use concentration as the predictor. I believe it's labeled DV in the data set, but concentration is the predictor, and delta QTC is the endpoint. Start off by assuming a linear structural model, but explore different assumptions about residual error patterns. So we assigned this last week, and some of you had some difficulties in getting started. So I'm going to show you how I might begin to approach this problem. I've also supplied this spreadsheet in the course site, which gives you a starting point. So what I've done is I've pasted the two columns from the data set, the DV column, or concentration here. It's not dependent variable for our current analysis, but it was the dependent variable for the concentration simulation. Anyway, we have these concentration data in nanograms per mil, and we have delta QTC data, dQTC. Concentration will be the predictor, dQTC will be the observed dependent variable. And so we're going to paste these in this spreadsheet here. It scrolls down for some 800 records. There's lots of data points here. And we're also going to specify a prediction. In our prediction model here, let me view the prediction model. Prediction model is a linear regression. We have an intercept, cell B3 here, a slope, cell C3, times concentration. It's as simple as that. We just have a straight line prediction model. In this case, we don't necessarily need to use a nonlinear regression technique for this model, but we're going to use this as a starting example. And given that linear regression, we create the prediction for each one of the data records. As you see, it's the same parameters in all cases. It's just the concentration is changing. And you'll see the same thing down here. And what we're going to want to do is to estimate these parameters, intercept and slope. So that's the starting point. You can look at the nonlinear regression workbook that we ran through in the last lab session to understand how to structure the objective function. And you could start with ordinary least squares. You could then move to weighted least squares, or even extended least squares, maximum likelihood methods, whatever objective function you'd like to code. But give it a shot. Make sure to describe the objective function for each data point, and then summarize that. And it's that summary objective function across all data points that will minimize using an iterative numerical technique. Okay, so that's a head start. This spreadsheet can be found in your project courseware site. Now, in addition to that one, if you get through that particular problem and you want to try something a little different, problem 1.2 is focused on a similar problem but a different endpoint. Now we have observed AST. This is a liver enzyme which appears to show some elevation here in a concentration dependent manner. We'd like to characterize that concentration response relationship, and so we'll look at this transferase enzyme activity versus the observed concentration of MI2005A. This case here, we might not necessarily assume a linear model. It looks like this response might rise sharply and then plateau, and really you might want to plot this on a semi-log plot, or even expand the x-axis to see what's happening at these lower concentrations. But the data indicate that there's some sort of relationship here. The variability seems to be a bit broader than what we saw with the QTC plot. But I'd like you to again explore maybe a nonlinear structure, an Emax type model for this relationship, and then also explore different assumptions about the residual error variance. Okay, that data set is also found on the course site under ast.csv. Okay, let's move on to the new topic now. We've been talking about maximum likelihood methods for population, for individual data, but now we're going to extend that to the population case. Before we get into the maximum likelihood objective function for population data, I wanted to describe a few terms that we're going to continue to use, and describe the types of data that we'd consider as dependent variables. So in population analyses, we can have either continuous or categorical endpoints using maximum likelihood methods, but the way that we approach these is quite different in the way we might structure the maximum likelihood objective function. For this course, we're going to focus on the continuous variables, and in PK, of course, that's typically plasma drug concentration, but we might have pharmacodynamic endpoints such as blood pressure, weight, QT, AST values, or lab values like that. Those are all continuous dependent variables. In later courses in our series, we talk about categorical dependent variables, and this is something that can also be handled through maximum likelihood methods, but it involves a different specification of the maximum likelihood problem. We can view these for dichotomous endpoints. These are the yes-no type events. Yes or no, an adverse event was experienced or not. Another is ordered categorical. These are typically used as rating scales for endpoints. A commonly used one is a 4 or 5 point pain rating scale. Count data are also common as a dependent variable in clinical outcomes. Here we might have, for example, a number of a certain event in a particular period of time. So, for example, the number of seizures per month might be a particular count variable. We can also analyze non-ordered categories. These are separate and distinct categories that are represented as the dependent variable, but they're not necessarily ranked in a particular order. And an example of that would be categories of the EEG sleep stages. And we can model transitions from one category to another using probabilistic type models. And then also time to event type measures, such as survival or time to the occurrence of some event of interest, is also a common clinical outcome. But again, these are all viewed in different categorical or probabilistic type sense that requires a different specification of the likelihood function than the continuous type endpoints that we're going to deal with in this course. Keep in mind, however, though, that even though we're not going to use or deal with categorical data as the dependent variable, we will discuss the use of categorical covariates as predictors of the continuous dependent variables. A few more terms to review. When we talk about repeated measures, especially in terms of population PK/PD, we're talking about measurements that are characterized by more than one observation per individual. And usually repeated measures in a clinical trial are taken longitudinally, that they're repeated measures taken over some period of time. The next two definitions are definitions that I've constructed to define sparse and extensive sampling, just because it's very difficult to come up with a formal definition of these because they depend so much on the context of the model and the study design. But a simple way to think of this is that if you have a sparse sampling situation, we're usually talking about a situation where you have too few samples in a single individual to characterize the model accurately. So you have to end up borrowing information from other individuals in the population in order to completely describe the structural model. Contrast that with extensive sampling, and when we think of extensive, that means you've got enough information, enough data points longitudinally over time to, within a subject, characterize the complete structural model. And this is the case that we run into with methods such as the standard two-stage approach, or with a lot of the individual data analysis methods. They're highly dependent upon having extensive data observations. Well, now that we've got those terms out of the way, let's discuss some of the analysis methods for population PK. And I'm going to go into each of these in a bit more detail, including naive pooled, naive averaged, standard two-stage, map Bayes, and then of course the nonlinear mixed effects models, which were really of interest in this particular course. Naive pooled. Naive pooled analyses are a very simplistic way to analyze population data. And simply stated, you just combine all of the data, no matter when they were sampled, across individuals or across experimental units. Often these are used commonly in non-clinical studies where you have individual animals contributing a subset of data, and then you pool them all together to create one picture of a single individual. You end up taking that pooled data set and fit the model to those data using any one of the least squares objective functions that we talked about. It's not a population objective function. We're using an individual level objective function where we're summarizing data points across the entire pool here from 1 to n, but treating them as if they arose from a single study unit or a single individual. And here you see an objective function for a weighted least squares analysis where you have the observed minus the predicted at each time point squared times the weighting factor here, which might be 1 over the observation. Naive pool is a quick and sort of a quick and dirty approach to analyze population data. It's not always the most accurate method, but it can be useful in some cases to provide initial estimates for a more complex analysis. Naive pooled analyses, if the sampling is balanced across all individuals, can give you estimates of the population mean parameters that are quite consistent with a more rigorous population nonlinear mixed effects analysis. But it completely ignores the assessment of variability between individuals, and of course the residual variability is also confounded because of that lack of accounting for inter-individual differences. But nevertheless, it can be a useful way to derive initial estimates for a more complex population-based method. Naive averaged is another variation of the same theme. This one requires a little bit more detail in the data. in that each individual unit should be sampled according to the same design. So if it's a PK study, each individual in a naive averaged data set will have samples at each time point. And what's simply done is that at each time point, the average across all individuals is taken, and a single data point represents that point for all the individuals. So you end up with really one data set equal to the number of sampling points in any one of the individuals. This one single individual is the mean individual, for example, and then the model is used to estimate the parameters for that typical mean individual. This is again a useful quick look at the data, but it can lead to bias if you have imbalance in sampling. For example, if some individuals at the later time points are missing data, that average can be skewed, and you end up trying to fit a model to something that's not really representing the underlying data. But sometimes it can be useful to generate initial estimates. Of the two approaches, naive pooled or naive averaged, I would actually prefer using the naive pooled approach as a quick method to obtain initial estimates for population mean parameters. Neither of these approaches address estimation of population inter-individual variability or residual variability. The standard two-stage approach is one where the data design is important. In this case, the design must be one where the sampling is extensive, such that each individual by themselves supplies enough information to estimate the model parameters for that individual. And so the reason this is called the two-stage approach is that first, the individual data profiles are analyzed and parameter estimates are obtained for each subject. Notice that this objective function is for a single individual across all data points within that one individual. That's repeated for each subject, and so now you have a complete set of parameters for each individual. And that set of parameters can be summarized in terms of a covariate relationship, such as this one here, where we have maybe the clearance across each individual viewed as some function of creatinine clearance. And then a second step might be to summarize all of those parameters in terms of a population mean, variance, and covariance across the population. Standard two-stage is really has been the gold standard for individual PK modeling, summarizing the data afterwards to derive measures of mean and variance. Can also be useful when you're interested in some of the population characteristics, although it has been shown to potentially lead to biased estimates of both the inter-individual and residual variability because of its two-stage nature. But overall, it's a very useful way to analyze data when you have extensively sampled profiles. Well, what if you have population data that are very sparse? How do you deal with those? One way to analyze that is using the map Bayesian estimation. Map Bayes stands for maximum a posteriori probability. That means that what we're obtaining here is the estimates of the individual parameters that are the most likely for that individual, or the maximum likelihood for that particular individual. But it's conditioned on estimates of other components of the model that are assumed to be known ahead of time. Those include the population mean parameters, the inter-individual variance or covariance, and the residual variance. So these are the population level parameters that are probably determined in a prior analysis, or maybe they're derived from the literature. But these are used to anchor then the fit of the model to each individual's data. And we'll discuss this objective function in more detail later, but you'll see here that we have a post hoc objective function for each individual, sub I. And that's simply the sum across all data points of the observed minus predicted squared divided by the residual variance plus the log of the residual variance. So that's just like the extended least squares objective function. Plus this additional term out here, this is your Bayesian penalty term, The first part is focused on fitting the model to the observed data, and the second part of this objective function helps to define how influential the population prior information should be in the estimation of these new individual parameters. The only thing that's estimated in this particular objective function is the individual random effects, the etas, and we'll describe what an individual random effect is in just a few minutes. But suffice to say that this is just the parameter that describes how an individual differs from the population mean. The other parameters, the population mean structural model parameters, the theta here, the residual variance, sigma squared, and the inter-individual covariance, omega, these are all known ahead of time, and they're not analyzed as part of this objective function. They're actually fixed to some prior knowledge. So this method, map-Bayes estimation, is useful for the analysis of sparse population data when the goal is just to derive individual parameter estimates. This is not a useful method for estimating population means or population variances. It's strictly focused on individual estimation from sparse population data. And in fact, this method is used quite commonly in a lot of the therapeutic drug monitoring software tools just because of that reason. You can estimate individual parameters given sparse data. There are a few words of caution in using this, which we'll address later, in particular concerns about when the individual estimate might be overwhelmed by the data or overwhelmed by the prior knowledge, and those are potentially points of concern if you're using this to guide dosing adjustments. So we've talked about methods for analyzing individual data, naive pooled population data, sparse data, but we haven't really found anything yet that allows us to take sparse data and analyze both the population level parameters, the means and the variances, as well as the individual specific parameters. So we're finally getting to that now. That's the nonlinear mixed effects model objective functions. And I'll describe how we can do all of that in one step in just a minute. Well, remember that our goal here, we stated in the first lecture, is to understand factors that lead to variability in PK and PD so that we can appropriately use the drug or appropriately design the next study. And the way that we want to do that then is to develop models that quantify the measurable sources of variability, those things that we can measure and predict, and also the unexplained sources of variability, those things that we can't predict, but we can at least quantify. If we can understand both of those pieces, we have a better understanding of how to control the variability. So a method that allows us to do that is nonlinear mixed effects. This is a one-stage method of simultaneous estimation of fixed effects and random effects parameters. I'll define those in a minute. But typically these methods utilize what's called a nested random error hierarchy, meaning that we have more than one level of random error, which is unlike the maximum likelihood approach for individual level data, where we had just a single residual error term. In this case, we're going to have a hierarchy, different levels of random variability according to different methods of grouping the data. In PK, most of the time we have at least the inter-individual level and the residual level. And these models employ maximum likelihood or similar estimation methods. Let's define a few terms. Fixed effects are those estimated parameters relating the observed or measured variables in the data set to the model prediction. So you can think of this as the parameters describing the structural model, clearance or volume, or maybe even the coefficients relating a covariate such as weight or renal function to a PK parameter. These are fixed effects. Random effects are those parameters that are estimated to quantify unexplained random variability. It could be quantification of how much an individual differs from the population mean, the inter-individual error. Or it could be an estimate of the error between the model prediction and some observed value, quantifying maybe the measurement noise, the process noise, so-called residual error. We can't predict these, but we can quantify their magnitude and describe the shape of these distributions, and even use them later on to simulate. But they're still random effects, because they may or may not be truly random variability, but for all intents and purposes, they're random in our view, because we have no way of predicting them. And again, the other characteristic is this nested random effects, or a hierarchical model, where we have two levels of random effects, at least. And level 1 in population PK models is the inter-individual variability, and level 2 is the residual variability. We'll see how those two fit together in just a moment. Of course, if you can group the data in different ways, you can describe random variability at multiple levels. We're not going to address that in this course. We do talk about that in next semester's advanced course. But you can see that describing these types of models does lead to more complexity, in that the random effects are not simply a single term added onto the prediction, as now we start identifying them with different grouping levels, whether that's between individuals, between occasions, between studies, and so on. We'll start with just these two levels. So let's look at this graphically. Here we see a plot of individual clearance for a population of individuals. This is drug clearance versus creatinine clearance. Creatinine clearance being a measure of renal function. And this is a simulated example, but it could be quite typical here that we see quite a range of variability in clearance values, ranging from somewhere at about 5 mils per minute up to maybe 60 plus mils per minute. But that variability does seem to follow a trend towards increasing clearance as creatinine clearance increases. And you'll see this red regression line here. That's the relationship, at least on average, for the typical individual, between clearance and creatinine clearance. We call that the typical value of clearance, and here we're expressing that relationship as a linear regression, with an intercept called theta 1 and a slope theta 2 multiplied by creatinine clearance. So it's a very simple linear regression model, kind of empirical here, but it gives us some idea of the relationship between drug clearance and renal function. Well, we can estimate these parameters for the population, and those estimates would give us a line that looks like this red line here. But one thing that's apparent pretty quickly is that there might be a few individuals that fall along that line, but there are plenty of individuals that do not, and they happen to be different from this typical relationship. Those differences are unexplained at this point, and we would treat those as individual random effects. So take, for example, this individual here, individual I, has a value, clearance, sub I, and that value lands somewhere away from the typical prediction line. In this case, he's got a clearance that's maybe less than the population value for a given creatinine clearance. And we would describe that difference as a random effect known as eta I. Go to the next slide, and you'll see that eta I is what makes this individual different from the population typical value, so that clearance for that individual is equal to the typical value plus an individual eta. Well, that same scenario holds for every subject in this population, and there's an individual eta for each one of these data points. Some of them are close to 0, or maybe exactly equal to 0. Some of them are small negative numbers, maybe large negative numbers, maybe large positive numbers. But there's a population distribution of this inter-individual error. We make an assumption in our parametric maximum likelihood methods that distribution follows a particular shape. And that is a normal distribution centered at 0 with a mean of 0 and a variance called omega squared. So the population distribution of etas is assumed to be normal, mean zero, variance omega squared. Great. So that describes, it quantifies the random variability. We can't predict why one individual is going to be different from another other than potentially measuring their creatinine clearance. But this remaining variability, although it can't be predicted, can be quantified, and we can use this. And it can even be estimated on an individual by individual basis if you have data from that particular individual. Well, let's say we could estimate that and make a prediction for the individual, and that's what this blue line represents. This is an IV bolus concentration time decay curve that represents the prediction for an individual subject having accounted for their individual fixed effects and covariates, such as creatinine clearance, plus the individual random effect, the eta. So all of that's already accounted for here. But you see that the prediction still doesn't go right through the data points. There's some noise around that. And the noise is known as the residual error. So the difference between this observed value and the corresponding predicted value, the individual predicted value, is equal to this epsilon. So C observed equals C IPRED plus a residual error. You'll notice that the subscript for epsilon is IJ, I for individual, J for sampling point. This refers to the notion that within each subject there are multiple data points, and each one of those individual data points is associated with a different residual random error. So the residual error is unique in that there's one for each observed data point in the entire data set, whereas the inter-individual random effect, eta, is denoted eta sub I, only one per individual. Now, depending upon how we group things, we could end up with more than one per individual, but for this particular, the base case we want to discuss here, we are going to specify a model such that the individual random effect is just one per individual, the residual random effect is one per observation. Well, that residual random effect has some distribution assumptions as well. And if you recall, when we derived the maximum likelihood objective function, we said that the objective function was specifically for normal measurement error or normal error. Well, we're going to make that same normality assumption here, where epsilon ij across all these data points are distributed according to a normal distribution with a mean of 0 and a variance called sigma squared. Okay, so now we have two levels of error. How do they fit together? First, let's go to the inter-individual random effect and derive that impact. So remember our relationship here between clearance and creatinine clearance. The red line indicates the typical value prediction, and at that particular point, the eta is equal to 0. The typical value is equal to the typical individual where they don't differ from the population mean. Eta is equal to 0 in that case, and that results in a concentration time profile that looks like this red one here. However, if we add the inter-individual random effect, and we model the prediction for a given individual, you'll see a different model prediction here. Eta I results in a prediction for individual I that differs from the population typical or population mean prediction. Again, there's a separate eta for each individual, for each parameter in the model, and those etas are assumed to be distributed according to our normal distribution, mean 0, variance, omega squared. Taking that a step further then, you see that even after accounting for the individual random effect, there still is some remaining variability unaccounted for by the model prediction. That's the residual error. And again, residual error denoted epsilon. The distribution of the epsilons is mean 0, normal, with a variance of sigma squared. So conceptually, this is how the random effects hierarchy fits together. We have the individual random effects nested within the prediction, but on top of that, after that's been accounted for, there still is a remaining residual random effect which usually describes the assay variability, process noise, and so on. Well, the random effects hierarchy, as we stated, was one that is nested with at least 2 levels of random effects. In population PK models, we're going to consider inter-individual variability and residual variability at least. Here we've described how those might enter into a prediction model for a particular concentration time observation point. First, we describe the variability in the PK parameters. So here we've described the individual clearance as something that's equal to a typical value of clearance. This is the clearance predicted based on population mean parameters or typical value parameters, potentially covariate effects. But it's the same prediction for all individuals in the population, except for maybe some individualization based on individual specific covariate factors. The random effect enters in this model in an exponentiated fashion, and we'll discuss why we might want to do that in a few minutes. But the important point to know here is that the individual clearance is made up of a typical component and an individual specific random effect, which is to be estimated from the individual's data. We can then take that individual clearance and include it in a prediction for the concentration time profile. Here we have a simple intermittent IV infusion model for a 1-compartment system, where we have a rate of infusion, K0, divided by individual clearance. We've got this exponential term, which represents the rise during the infusion time. Time t is time of infusion. And then the decay here according to time post-infusion. This prediction model does not entirely explain all of the variability in the observed data. And so it's necessary that even though we have inter-individual random effects, it's necessary to include a residual random error term. Remember, the residual random error here is for each individual I and each sampling point j, whereas the individual random effects are just individual specific. We can nest those together in a nested random effects model, where you see here the observed data equal to some model prediction, which is a function of independent variables, time, infusion rate, typical value parameters, inter-individual random effects, and all of that still doesn't account for the variability, and we have the residual error term. Our assumptions for the parametric maximum likelihood approaches here are that the etas are normally distributed with mean 0 and variance omega squared, and epsilon similarly normal, mean 0, variance sigma squared. Inter-individual variance models, just like residual variance models, can take different structural forms. If you recall, in the maximum likelihood lecture, we explored methods for determining the pattern of the residual variability, and one of those was by looking at residuals versus predicted plots compared to weighted residuals versus predicted, and the residuals versus predicted was indicative of the pattern of the variability in the data. Well, we don't have a similar residuals plot on the individual random effect side, but we can model the individual random effects according to different assumptions about their distributions, or different assumptions about the pattern of the variability between subjects. The first one is relatively straightforward, and this is a constant variance, or a homoscedastic inter-individual variability model, where we have individual clearance here represented by some typical value prediction. Theta 1 and theta 2 are fixed effects parameters relating creatinine clearance to clearance. And you see that this individual random effect enters once per individual in a constant additive term. There's a proportional variability model, which is also known as a constant coefficient of variation. And this is one where the individual clearance is equal to, again, some typical population value. But now the inter-individual random effect is not simply additive. It increases proportionally with the value of the predicted clearance, or proportional with the value of the typical predicted clearance. So in this case, you'd see that as typical clearance increases, so does the inter-individual random effect. That's a reasonable assumption in population methods, which usually PK parameters are sort of right skewed or have tails to the higher end of the distribution. Another way to model that is through an exponential or a log normal distribution, which approximates a constant coefficient of variation at lower measures of inter-individual variance. Again, you see the individual clearance described by some typical value with an exponentiated now inter-individual random effect. This is analogous to saying that on the log scale, the log of individual clearance is equal to the log of the typical value plus an additive eta. So we have a log normal distribution. Again, this is a typical assumption made about pharmacokinetic parameters. It usually holds pretty well and is a useful point, potentially a useful starting point for describing inter-individual random effect distributions for PK parameters. We'll talk about diagnostics for the inter-individual random effects and potentially the appropriateness of the selected distribution. But one thing to remember is that in each case here, the eta I, the individual etas, are always assumed to be mean zero normal with variance omega squared. And it's just that they are used in either a proportionality constant or in some exponentiation here that allows the inter-individual variability to appear non-normal or non-constant. But the etas themselves are always normal, mean zero, variance omega squared. That's an important concept, and it's one of the key assumptions in the parametric methods that we're using. It's also an assumption that we can easily check in the modeling process, and we'll discuss that in more detail later. Now let's go to the residual level. Residual variance models are very similar to what we discussed on the individual level data using maximum likelihood in the first lecture. I'll just review a few of these written in the population context here, but the concepts are essentially the same. So the first is a homoscedastic or constant variance model, where we have the observed data here. The y represents the data, yij equals fij. Fij is the model prediction for individual I at time point j. This prediction includes the individual random effects plus a residual random error. That residual random error enters additively here. It's a constant variance assumption. It's possible, especially in pharmacokinetics, that the residual error is actually not constant and proportional to the model prediction or the observed value. And that's expressed here in this proportional model, where the observed data for individual I sampling point j are equal to the prediction for that same individual in time point, times a proportionally increasing residual random effect. Again, the epsilon ij are assumed to be normal, but they're multiplied through by this proportionality constant equal to the model prediction, which allows the observed variance and the model predicted overall variance to increase as a function of the model prediction. Another way to state this is to use an exponential relationship, which gives you a slightly more dramatically increasing variance as you increase the model prediction. At lower variances, this does approximate the proportional constant coefficient of variation. Again, where you have the observed data, the prediction, and an exponentiated residual random effect. And actually, in order to truly implement this in the approximate likelihood methods, such as the ones we'll be discussing in the NONMEM software, you have to transform both sides, and it's really equivalent mathematically to log transform this expression. So you end up with the log of the data equals to the log of the prediction plus an additive residual error. So again, we're modeling a log normal residual error. Mathematically, these appear to be equivalent, but the way that the likelihood approximations are made in some of the classic methods in NONMEM, this first expression really doesn't give you a full exponential. In order to achieve that, you need to use the log transformed expression. I'll explain why in a few minutes. And then, of course, we can have more than one level of residual random effect, or more than one type of residual random effect. In this last model here, we have a combined additive and proportional residual error. So we could imagine that the observed data are characterized by variability from multiple sources. One of them might be the assay error, and oftentimes that's the proportional component for most analytical assays. But there may be other sources of noise, including process noise, errors in recording the data, errors in conducting the experiment, and these things are oftentimes constant or additively included in the model prediction, and that would be represented by the second epsilon here, epsilon 2. So epsilon 1 is a proportionally increasing residual error, whereas epsilon 2 is a constant residual error. And if you'd like, you could have another term. Really, this is up to the modeler to describe, but these are some of the most common representations of the residual variance models. Nonlinear mixed effects methods can be categorized into two major headings. One is parametric methods, and the other is nonparametric methods. And this really has to do with the assumptions around the individual random effects and also some assumptions about the residual random effects. It has nothing to do with the assumptions about parametric or nonparametric forms for the structural fixed effect model. In the parametric methods, there's an assumed distribution for the inter-individual random effects, and we've been discussing that, assuming parametric methods, from the start of this lecture, where we've defined the inter-individual random effects by a normal distribution with a mean 0 and a variance omega squared. Well, this applies in all of the classic NONMEM methods, first order, FOCE, Laplacian, the NLME method in R and S+. Even Bayesian hierarchical models may make this assumption, as well as other tools. That's in contrast to the nonparametric methods, which make no assumption about the distribution of the inter-individual random effects. And in fact, the inter-individual random effects are typically allowed to float to wherever they need to be for the model to fit the data. But there is some constraint required, otherwise you'd have a completely unidentifiable system, and that constraint is on the residual error. In these methods, it's typically conducted such that the residual error is fixed to some pattern that represents the assay error, or the assay error times a proportionality constant. Now that's a constraint that is necessary in this particular type of nonparametric analysis. It allows the individual etas to be discretely estimated one per individual, and there are several methods, NPEM, NPML, and PAG. These are all methods that allow for that. NLMix is a method that also allows for nonparametric estimation of the random effects, although they're modeled with a continuous smooth density rather than discrete density. But the point to be made here is that even though have a method that's called nonparametric and another one that's called parametric, each method makes assumptions. In the parametric method, there are strong assumptions about the distribution of the random effects, both inter-individual and residual. In the nonparametric method, the assumptions about the shape of the inter-individual random effects are relaxed, but there is an assumption that the residual error is known and the residual variance pattern is known. at least up to a proportionality constant. And sometimes that's a bit of a stretch too, because residual error, it comprises not only assay noise, but as well as process noise from incorrect recording of data, experimental design error, and conduct error, the model misspecification as well. So there's other things that factor into that residual noise. And under the non-parametric methods, those are assumed to not exist, and essentially that sort of noise is passed on to the individual level. So there's assumptions both ways. It's up to the modeler to be aware of what those assumptions are, apply the method that's most useful for their intended purpose. And when we talk about simulation, it'll become apparent why the parametric method is oftentimes preferred when the purpose of modeling is to develop a simulation model. More on that later, and we'll discuss some of the implications as we work on hands-on projects throughout the class. So next we'll shift gears to derive the objective function now for the population estimation case. Remember the individual level objective function? This was based on a normal probability density function with the assumption that the error was normally distributed, and that was described by some summation across all the data points of the observed minus the predicted squared, divided by the variance plus the log of the variance. Well, let's restate that now for a population model. If you think about this conceptually, don't worry so much about the statistical notation, but it's really the same problem. We've got observations, we have predictions, and we have variability. The difference here is that the variability is comprised of at least two components now. The inter-individual variability and the residual variability. But other than that, it's the same problem. So here's the objective function in a population case for an individual. We've got a -2 log likelihood of the data for an individual, yi, given the independent variables x sub I, the population mean parameters, theta, and the variance for that individual, c sub I. Now, C sub I is a matrix, and it describes all sources of variability, including inter-individual and residual variability. So we take a summation across all the points for that one individual here of the observed minus the predicted squared. You see here it's a vector transpose times the vector. Essentially here what we're saying is the observed minus predicted squared times 1 over c sub I, or in other words, divided by the variance, plus the log of the determinant of the individual covariance matrix, or in other words, conceptually speaking, the log of the variance. Just like this maximum likelihood objective function for single subject data, except we're now writing it in matrix notation to accommodate the population case. So then if we take this individual and we want to obtain the overall objective function for the population, how do we get from one to the other? In the log domain, we then add up each of the individual contributions to the objective function to sum for the total population objective function. So now it's the log of the likelihood of all the data, not just y sub I, across all of the independent variables, population mean parameters, and covariance matrices. Summing across individuals and data points, then we have the same expression, the observed minus the model predicted squared, divided by the variance, plus the log of the variance. So conceptually it's quite similar. What we now need to understand is how does this one term c sub I enter in the model? How does this variance enter this, and what does it really mean? The individual variance covariance matrix, C sub I. This is how we can capture in one term in the previous expressions all sources of variability. And you see here that it's made up of two pieces. There's this G omega G piece, and then the H sigma H piece. The first term represents the contribution due to inter-individual random effects. The second, due to residual random effects. G here is a matrix of partial derivatives of the model prediction with respect to eta. So here we see the individual contribution of the individual random effects to the overall weighting. These partial derivatives determine how influential a given parameter's random effect might be at a particular time point in the model prediction. It's scaled by the magnitude of the individual variance, or in other words here, by the omega, the population inter-individual covariance matrix. So the partial derivative matrix defines where in the concentration time curve the individual random effects are most influential, whereas the omega matrix determines the magnitude of that impact and how large that variance might be. H is the matrix of partial derivatives of the model prediction with respect to epsilon. And so this describes the impact across the concentration time profile of the residual error. And as we said, in cases where that residual error is non-constant, proportional or exponential, there's going to be a different impact at different points of the concentration time profile. That is scaled then by a measure of the magnitude of the residual variance, sigma, which is the covariance matrix for the residual error. And usually we model sigma as a diagonal matrix, and I'll explain that in a moment. But the take-home message from this is that this individual variance covariance matrix represents all sources of variability and is used to weight the objective function in a population case. This is what differentiates a population model from an individual fit or naive pooled fit. And really, it's this piece here where we're accounting for the inter-individual variability and the correlation within subject of those random effects. Okay, let's take a minute to talk about the pieces that make up that individual covariance matrix. One of them is sigma, the covariance matrix for the residual error. And so sigma is a matrix, and for all these matrices, we're going to view them in the same way, in that the diagonal terms here, sigma 1,1, sigma 2,2, these are variances, and the off-diagonal terms are covariances. So sigma 1,1 is the variance of residual error epsilon 1. Sigma 2,2 is the variance of the residual error epsilon 2. Well, you think, well, why do we have two of these? It's because we might have a model that specifies different sources of residual error. So for example, sigma 1,1 could be the variance of a proportional component in a combination residual error model. Sigma 2,2 could be the variance of the additive component of a combination residual model. You could also view this in terms of a multivariate endpoint. Maybe we have parent and metabolite plasma drug concentration data, and sigma 1,1 represents the residual error variance for the parent drug, sigma 2,2 for the metabolite. Well, that's nice. That's easy to understand what the variances mean. What do the off diagonals mean? And in this case here, it's probably only relevant when we're dealing with these multivariate type models where you have parent and metabolite data sampled at the same time point. It's likely then that if there's residual noise associated with one, that noise might be correlated with the other analyte. And we can model that correlation through this covariance term, sigma 2,1. The upper triangle here, sigma 1,2, that's the same value as sigma 2,1, and you'll see the notation that we use commonly is just a lower triangle, the lower left half here. We ignore the upper triangle because it's the same value as the lower. Most of the time, unless we have this multivariate type endpoint, we ignore the residual correlation, and we model these off-diagonal elements fixed to 0, assuming that there is none. Okay. The inter-individual covariance matrix, omega, is constructed in a very similar way, although it's representing a different level of variability. And here the dimension of this matrix, or the diagonal length, represents the number of inter-individual variance terms in your model. So if you have a pharmacokinetic system with maybe a 3-parameter compartmental model, such as a Ka, a clearance, and a volume, you might have a random effect associated with each one of those. And so it could be that omega 1,1 is the random effect variance for Ka, 2,2 might be for clearance, 3,3 might be for volume of distribution. So that represents the variance of the random effects on each of those parameters. But then the off-diagonal elements represent how these two parameters co-vary in the population. So there's somebody with a large volume, a large Ka also have a large clearance, or a large clearance result in a large volume of distribution. So these covariance terms allow us to model some of these very realistic covariances between inter-individual random effects across the PK parameters. Of course, if we assume a diagonal matrix only, then we'd fix these off-diagonal elements to 0, and what we would say is that these are independent random effects, that they don't covary, and that there's no constraint on what the random effect on Ka should be when compared to clearance and so on. That's not a very realistic situation. In fact, most of the time there is some covariance between these terms. And so we do our best to try to capture that in the mixed effects model development. This next plot reminds us of the fact that there may be correlation in these inter-individual random effects. And so you can view this like the matrix we just looked at, where really we're not concerned with the diagonal, but this represents a scatter plot matrix where we have eta 1, 2, 3, 4, which might come from a PK structural model that has 4 parameters, let's say clearance V1, V2, and an intercompartmental clearance for a 2-compartment IV system. And you can see from this pattern which random effects are correlated with each other. And there's some clear, strong correlation here between eta 1 and eta 2. Although when you look, for example, between eta 3 and eta 4, or eta 2 and eta 4, there's not much of a strong relationship. This is a useful plot to explore the random effects. And what we've got plotted here, just to remind you, is the individual specific random effect. Each one of these points represents a single subject, and the correlation between eta 1 for clearance versus eta 2 for central volume of distribution. What we'd like to see is that this block structure with the covariances is something that we've accounted for in the model. Now, this is not a diagnostic plot. It's really just more informative about where the correlations might be. And we'd like to construct an omega matrix in our model that reflects this. So if we had constructed a matrix that was assuming all the off-diagonals were 0, it wouldn't necessarily be appropriate for this model, because we do see some pretty obvious correlations here. Eta 1, 2, eta 1, 3, eta 2, 3. There's some correlations between these. Well, we usually specify these as a covariance, but this is a useful formula to convert to a correlation coefficient. You take the covariance term between parameters A and B, divided by the square roots of the corresponding variances, and that gives you a correlation coefficient. The correlation coefficient will run from -1 to +1. The closer you are to an absolute value of 1, the more highly correlated the two random effects would be. And when you reach something, 0.95 and higher, that's telling you that those random effects are not uniquely identifiable. Next, we'll discuss the prediction model. So we've reviewed where the objective function comes from, but we haven't really talked about where the prediction comes from with respect to the population model. So what we've done here at the top is to write this model in a very general form where the observed data Yij are equal to some model prediction Fij, which is based on population mean parameters theta and inter-individual random effects eta, plus some residual random effect. Well, when the structural form Fij here is a nonlinear model, we actually end up with a difficulty in that the overall likelihood here is problematic because we have a prediction which is nonlinear with respect to the inter-individual random effects. And so what we want to do is to be able to solve this analytically. We have to marginalize that random effect or integrate out the random effect. This is not possible when the random effect enters nonlinearly unless we make some approximations. Well, in fact, there's two potential solutions. Whenever there's an analytically intractable problem in mathematics, you can either come up with a new statement of the problem that's an approximation that is now analytically solvable, or you could have a numerical solution of that problem, which would be still the analytically intractable model, but would just be solved using a more approximate numerical method. Well, in the early population kinetic algorithms, one of the first methods was a so-called first-order approximation, and this was one that instead of solving the true model, makes an approximation to the model and then solves the approximation analytically. And the approximation made here is that the eta values here, which enter nonlinearly, are marginalized by taking a first-order Taylor series approximation with respect to eta. And so if you apply that first-order Taylor series to the model above, you end up with a model prediction as a function of the population mean parameters, plus the partial derivative of that prediction with respect to eta, the first derivative, plus epsilon, plus this approximation error. We then evaluate that first order expansion at the expected values for each of the random effects, and you see here now we have the model prediction at the mean value, the partial derivative times eta at its expected value. Well, what's the expected value of eta? 0. Remember, the mean of the etas is assumed to be 0. The expected value of epsilon is also 0. And then the expected value of this approximation error, which collapses down to now an expected value of the prediction, which is the model prediction plus the approximation error. If we're pretty optimistic about this, we'll assume the approximation error is also 0, so the model prediction collapses down to one that is entirely based on the population mean parameters only. There is no individual specific parameter in the first order approximation model prediction. So when we go back and look at that objective function, this term here, f of xj theta, or f of xij theta, is purely based on the population mean parameters for the FO method. Okay, we'll talk about some alternative approximations that might be a little more rigorous than the FO. But this is the classic method. This was the original method developed for population PK modeling. And of course it's had its criticisms because of the large assumptions that are made here, and also the performance under certain cases. So the FO method is notorious for poor performance when the individual parameters are well defined. So when you have relatively informative sampling designs about individual parameters, the FO method does not perform all that well. And in fact, these days there are much better methods that have become more of the bread and butter work. But the FO method was where it all started. Let's think of some other ways we could improve this approximation. So the FO is the original classic method which is evaluated at eta is equal to 0. In that particular method, there is no estimation of the inter-individual random effects. Every individual has the same parameter predictions, except for what might be uniquely individual because of individual specific covariate factors, but there is no individual random effect estimated in the FO method. The variance of the random variability, omega, or the omega matrix covariance, and the residual random effect, sigma, random variability, sigma, are both estimated. They're part of the objective function, right, which I just showed you. But the individual random effects themselves, that individual specific difference, is not estimated. In order to get that individual estimation step, you run something called post hoc in NONMEM, and this is equivalent to the map Bayes objective function, which we mentioned earlier. Recall that in map Bayes, you're required to have prior knowledge or fixed values for the population mean parameters, the inter-individual covariance, and the residual variance. From that, the individual random effects are estimated. Well, that's what we need to do under FO if we want to get individual level parameters. That's not so appealing, and the problem with that is that the individual parameters don't play into the estimation of the population level parameters. That assumption that all the individuals are the same is really not valid, and it ends up sometimes with some biased estimates. So an improvement to that is another method which uses a first order Taylor series expansion, but it's a conditional estimation method in that expansion is evaluated not at eta equal to 0, but at eta equal to a conditional estimate of that individual random effect. So your best estimate of the individual difference from the population is incorporated as part of the search. So if we go back to that specification up here, instead of evaluating this at eta I equal to 0, it's evaluated at eta I equal to the individual eta, which requires then within each iteration, in each evaluation, that there has to be a search for the individual specific parameters as well as the population parameters. Depending upon the number of individuals in the data set, that can dramatically increase the run times. And so really, although it's a much more accurate approximation, it comes at a computational cost compared to the FO method. These days, though, for most problems, it's quite doable, and it's become with the interaction method, which I'll mention later, FOCE has almost become the standard place to start. There are other approximations. One is the Laplacian approximation. This is a second order expansion known as the Laplacian expansion, which is also evaluated at the conditional estimates of the individual etas. There are methods known as hybrid methods which allow you to specify some of the random effects in the model under the FO assumption and others under conditional estimation methods. And there's really no theoretical advantage for this. It's just provides you a computational advantage rather than going with a full conditional estimation method. And then there's the eta epsilon interaction. This allows the individual specific prediction to partake in the weighting function when the residual variance model happens to be non-constant. So when the residual variance is some function of the model prediction. I'll describe that one in more detail in a couple of minutes. So remember, we said that under FO, the only way to get the individual estimates is to run a post hoc step. But you've got to be cautious with that. Here's an example of why you need to be cautious. The individual parameter estimate can be dominated, even when the data are very sparse, by the data. The converse is also true, that when the data are extensive, even the parameter estimate can be dominated by the prior. And it really depends on the relative magnitude of the inter-individual variability versus the residual variability. So let's consider the case where omega is much larger than sigma, and that's the case where inter-individual variability is quite large. relative to residual. Well, conceptually speaking, that allows more room to move on the individual random effect side. There's more flexibility there. And so what happens is that whatever the individual's parameters need to be to fit the model to the data, there's no constraint or little constraint, and those individual parameters can move very far away from the population mean or the prior. And so you end up with estimates of the individual parameters that are dominated by the individual's data. Okay. You can also see that here in this objective function. If omega is very large, so 1 over omega here in this penalty term, well, this piece is already practically minimized because of the large size of the variance. So it doesn't really matter how far away these etas get from 0, because this penalty term is pretty much minimized due to the large omega estimate. And so you can end up with individuals that are quite different from the population mean in order to fit the data. Sometimes that can be viewed as an overfitting of the data. When the population prior dominates, well, that happens when the data themselves are not as trustworthy, where the sigma squared is relatively large relative to omega. So omega doesn't allow for a large range of variability for the individuals to be quite different from the population. And also sigma being larger here really unweights the data in this objective function. So sigma squared becomes large here. Then the individual etas really won't be driven so much by the data. They'll be driven more by how far they differ from the population mean, or how far the individual eta might be from 0. And in that case, then they're constrained closer to the population expected value of 0. That's so-called eta shrinkage. Okay. Next to this topic of eta-epsilon interaction, under FOCE and now under really all methods in NONMEM, you can allow for an interaction between the inter-individual random effect and the residual random effect. And this only applies to those models that use a residual variance structure which is dependent upon the model prediction. So here's an example of a proportional residual error. I've got the observed data equal to the predicted plus a proportional residual variability. Now I specifically have denoted this first term as Fij sub A and the second one as Fij sub B. That's because they play a different role with respect to random effects according to these different methods. So in the first case under FO, both of these predictions are evaluated at eta equal to 0. That's the very crude assumption that all the individuals are the same. There's no inter-individual random effects. And so there's no difference there between the two. Under FOCE, though, the prediction, as I showed you before, is evaluated now at the individual specific random effects. So this model prediction, f of ij a, is evaluated at eta equal to the individual eta. But when the weighting is calculated and in a proportional or exponential residual error, the component of the prediction used to scale the residual error is actually evaluated at the population expectation, or eta equal to 0. It seems a little bit counterintuitive, but it's just a simplification that was implemented under the FOCE method. Well, probably the more complete or more accurate way to do this would be to allow the individual prediction to take part in both the prediction part of the model and the residual variance component of the model. And that's what happens under FOCE interaction or Laplacian interaction and so on. What we have here then is an interaction between the individual random effects in the prediction and epsilon. They're both a product here, so that's why we call it eta epsilon interaction. And this allows now the individual specific prediction, which is presumably a better prediction of the individual's data than the population mean. It allows that individual specific prediction to be the driver of the proportional variance component of the model. So that's the interaction effect. Well, now that you understand where the objective functions come from and how we specify the prediction model, which approximations we make to the likelihood, we have to think about diagnostics, because understanding the methods, we also understand the assumptions, and some of those assumptions can be evaluated through model diagnostics. So let's run through a few of these now, and from a theoretical point of view, and we'll see this over and over again when we run the examples as part of the classroom projects later in the course. So I'm going to talk about a variety of diagnostics for population nonlinear mixed effects models. The first I want to talk about are residuals for the population case, and specifically weighted residuals and conditional weighted residuals. CWRes stands for conditional weighted residuals. In NONMEM 6 and earlier, the weighted residual for all methods was one that was constructed according to the FO assumptions. That means that the individual random effects never played a role in calculating the weighted residual. And here you see that the expected value under FO is evaluated at the independent variables, the population mean parameters, and eta equal to 0. The individual covariance matrix, remember that's the G matrix times omega times the G transpose. Well, that's evaluated at eta equal to 0 also. And so your weighted residual then is simply conducted under the FO assumptions. Now, this is the case, or was the case, for the weighted residual no matter what estimation method was used. So even under a conditional estimation method like FOCE or Laplacian, the same weighted residual was calculated. So in order to get around that, a new residual was developed called the conditional weighted residual, which was more consistent with the conditional estimation assumptions. And that is, it was evaluated at the individual specific value of eta for both the model prediction and for the individual covariance matrix. So the conditional weighted residual is the observed value minus the expected prediction at the individual random effects divided by the square root of the overall variance evaluated at the individual random effects. So this is exactly consistent with the FOCE method and is a much more appropriate diagnostic than the standard weighted residual. So to summarize on this term, the weighted residuals is the proper diagnostic for the FO method and FO method alone. It's not the proper diagnostic for any of the conditional methods. CWRes, or conditional weighted residuals, is more appropriate there. This can also be useful under FO, though, however, to investigate the possible impact of conditional estimation. So if you're stuck with a problem that runs very slowly, it's a large, complex model, large data set, you might be tempted to run the FO method because it's just simply quicker. But you want to know, well, how bad is that approximation here? How careful do I have to be about interpreting the results? And what CWRes allows you to do is you can calculate that for the FO model, and you can calculate weighted residuals for the FO model. And if the distributions of those are similar, then it could be that the FO method is appropriate for your problem. The assumptions are not too unrealistic for that case. However, if weighted residuals and conditional weighted residuals differ greatly, that's evidence that the FO method is not appropriate for this problem. Well, the nice thing is that in NONMEM 6 and earlier, you used to have to do a lot of data manipulation and post-processing to generate those conditional weighted residuals. But in NONMEM 7 now, this is automatically part of the output, and there's a variety of variations of that conditional weighted residuals depending upon different estimation assumptions. And you can see more about that in the NONMEM help topic that's known as PRED, RES, WRES. And also there's a nice presentation on this topic from Angie Hooker that was presented at the PAGE meeting in 2006. So we're going to use conditional weighted residuals as the diagnostic for conditional estimation. Well, other components of the diagnostic. Well, one of them that's not very useful on its own, but it's reported as part of the output, is the minimum value of the objective function. And right here I've got replicated just the way it looks in the NONMEM output is the minimum value of an objective function for a model. 2433.919. Really it's meaningless by itself. But as we saw with the regression spreadsheet, is that as we improve the model fit under the same estimation method, this objective function will drop, and we can compare competing models within the same estimation method by using statistics that are based on this minimum value of the objective function. Another useful output is the final estimates of the parameters, and these are useful for a reality check. Do the final parameter estimates make sense? We can also evaluate them for possible boundary conditions, and we'll discuss that more when we get to hands-on work. But here you see how they're listed. We have theta, the vector of fixed effects, so they're just numbered 1 through n. This is NONMEM output, and you'll see that theta 1, 2, 3, 4 here represent the fixed effects parameters. It might be associated with clearance V1, V2, and intercompartmental clearance. And then you have a random effects matrix here, omega, which represents the covariance of the individual random effects. Again, remember we have a symmetric matrix here, so we're only going to discuss the lower triangle. The upper triangle is the same. The variance terms are on the diagonal, and the covariance terms are on the off diagonal. And here you see that this estimate results in covariance terms that are all 0. And that's because of this particular option that was chosen for this model, which actually forced those to be 0. And the only thing that was estimated was the diagonal variance. So this assumes there's no covariance between any of the random effects. And then finally, there's the covariance matrix of the residual random effects, the epsilons, known as sigma. This one has just a single term, so it's a variance of sigma. It could be the variance of a proportional error term. In addition to the final estimates, we also have standard errors of the estimates. These are standard errors obtained from the asymptotic covariance matrix of the estimates. This is based on statistical theory. It relies heavily on the normality assumptions for maximum likelihood. But these are standard errors that represent the precision of the parameter estimates, or how well do we know the parameter estimate. We'll look at these in more detail later. Another output is the eta bar diagnostic. Eta bar is simply the arithmetic average of the individual etas. According to our assumptions, the mean of the etas should be 0. And so what we're doing here was we're just testing to see if the etas are centered at 0. So you'll see this diagnostic eta bar, and with it you'll see separate values. Each one of these represents the mean of one of the eta terms. So it could be the mean for eta for clearance, V1, V2, intercompartmental clearance, for example. And it's difficult from looking at these to tell if they're different from 0. They're small numbers. They're close to 0. But are they really different from 0? And that's where this p-value comes in. The p-value is for the test given that the null hypothesis that the true mean is 0. If this p-value is significant, it might indicate that the etas are significantly skewed from 0 or not centered at 0, and that's a violation of one of our assumptions. This is not a test of a normal distribution, however. It's just a test that the random effects are centered at 0. Diagnostic plots are a very important part of the model evaluation. And I'm going to run through some of the typical ones. We've looked at these on the individual case before. We'll look at them now in a population case. For a PK system, here's a very useful one. It's the observed and predicted values versus time. You see the predicted values are the blue circles with a line. The observed values are indicated by their ID number. You want to see then, obviously, that the predictions run through the middle of the observed data. We can look at observed versus predicted values, observed versus population typical prediction, that's usually called observed versus pred, or observed versus individual specific predictions, which is observed versus IPRED. The difference between these two plots is that the one on the left is evaluated at eta equal to 0 for the model prediction. The one on the right is evaluated at eta equal to the individual specific value. Of course, the one on the right is always going to look better, but you need to look at both of these plots because sometimes the individual etas can result in an overly optimistic goodness of fit, and you need to balance that with the population typical prediction as well. Again, we want to see these values centered around this line of unit slope. There can be some deviation around that line as long as it's balanced. And you get to see here some of the pattern of the variability. You know, this one shows that proportional relationship where the variability is higher at the high end. It's also pretty clear on the IPRED plot. We can look at residuals and weighted residuals versus prediction. These are informative just like they are at the individual level. Here you see the reference line 0 with a relatively even scattering, and it appears to be a proportionally increasing the variance. When the weighted residuals are calculated, that variance seems to be blunted a little bit, and now we have more of a constant relationship of the weighted residuals across the prediction range. This would indicate that you probably have a decent weighting scheme for this analysis. We can also look at these two versus time. Especially in PK systems, this is useful, whether it's time in a dosing interval, which might be informative about the structural model specification, or time over the duration of the study, which might be indicative of any time-dependent changes in PK. And then, of course, conditional weighted residuals if we're running a conditional estimation method. And you see versus prediction or versus time here, a relatively evenly scattered conditional weighted residual. These are decent diagnostics for this particular model. They're centered at 0, no strong runs of negative or positive residuals. Another thing we might check is the distribution of the conditional weighted residuals, and here we're checking that versus a theoretical normal distribution in a QQ plot. And to the right, we're looking at a histogram of those conditional weighted residuals, which looks quite normal. Again, this is consistent with our assumption of normal error that we use for maximum likelihood of continuous data. We also have the assumption of mean zero and normally distributed inter-individual random effects, and here's another way to check that. We used eta bar to check the central tendency, but the shape of this distribution is best viewed in diagnostic plots like this. You could do the QQ norm or just a simple histogram like these. The one on the left here indicates an eta distribution that is skewed and not consistent with our assumptions of normality, whereas the one on the right is nicely centered at 0 and symmetric, approximately looks kind of like a normal distribution. It looks quite good. The difference between these two plots is the first. These are both from the same data set. It's just that the model on the left has not included the individual specific covariate predictors, whereas the one on the right has. So you can see that misspecification of the inter-individual random effect distribution doesn't necessarily mean that your data set is hopeless. It means that you maybe have to specify some improvements to the model before you can check that assumption of a normal inter-individual random effect. And remember that although it's not a diagnostic, this sort of a eta pairs plot is useful to guide the determination of which elements should be modeled in terms of covariances in the inter-individual covariance matrix. Next, we'll talk about a few of the goodness of fit summary statistics that are used to compare models. One of them is the Akaike Information Criterion, the AIC. This is a useful tool to compare models. There are no requirements for the models to be related in any way. The only requirement is that they're constructed on the same data set and also under the same estimation method. So the lower the AIC, the better the fit to the data. And simply put, the AIC is equal to 2 times the number of parameters plus the minimum value of the objective function. That term there, 2 times the number of parameters, is sort of a penalty so that you don't overfit the data with too many parameters. Model A here is in an example has a minimum value of the objective function of 2469 and 12 parameters. That gives us an AIC of 2493. Model B, on the other hand, has a slightly lower objective function, 2454, but to do that, it required 2 more parameters, 14 parameters now. We calculate the AIC for Model B, and that results in 2482. Well, even though there's a penalty for those 2 additional parameters, the AIC as a criterion identifies that Model B fits better than Model A. So that's one criterion we can use to assess goodness of fit and to compare models. There's no statistical inference or statistical significance determined here under AIC. It's just a model selection criterion. And this is just one criterion out of multiple criteria that you should use to compare models, including all the diagnostics that we just discussed, as well as some of the model evaluation and model qualification methods that we'll talk about later in the course. So it is possible to make inferences from the models, and it could be through hypothesis testing or from deriving parameter estimates and confidence intervals, which could be used to support inferential decisions. Hypothesis testing is a risky thing in this sort of modeling, but hopefully the comparisons are pre-specified. The alternative models are also specified. And you use various methods. One of them is called the likelihood ratio test. A more compute-intensive method is called the randomization test. We won't discuss that one now. You have to be concerned about things like multiple comparisons. And there's all kinds of caveats with applying hypothesis testing. And it's certainly not as useful when the objective is just simply a learning objective. But if you want to do it, here's what the likelihood ratio test is. The likelihood ratio test is a way to make a statistical inference comparing 2 models that are nested. And when we say that models are nested, that means that one model is a subset of the other. Well, from statistical theory here, we know that minus 2 times the difference in the log likelihoods from nested models follows an approximate chi-square distribution. So the objective function from the full model, or minus 2 log likelihood, minus the objective function from the reduced model, is approximately chi-square distributed, with degrees of freedom equal to the difference in the number of parameters between the 2 models. So we might compare 2 models to make a statistical inference, or to test the statistical significance of a particular model feature. Here's an example. Our full model is one for clearance, which includes an intercept or some typical clearance, some additional effect on clearance due to smoking, and an inter-individual random effect. The minimum objective function here is 483. In the reduced model, we've removed the smoking effect, and now clearance is just a function of some typical value and an inter-individual random effect. Well, that removal of smoking has now increased the objective function to 490. So the change here is 7, an increase of 7 units. And we can then take that critical value and compare it to a chi-square distribution. If you look at the back of a statistics book and look at chi-square distributions under various degrees of freedom, you'll see that for one parameter difference, or 1 degree of freedom here, theta 2, that's just one parameter, the critical value at p less than 0.05 is 3.84 units. And at 7, we've exceeded that. So we could say that this smoking effect is statistically significant with a p-value less than 0.05. However, if you were making multiple comparisons or wanted to be a little more conservative, you might adjust the p-value. And if you're looking at a p-value of 0.005, the critical value is now 7.8 units, which the critical difference here does not reach. So it's a little bit fuzzy here when you're applying the likelihood ratio test to determine statistical significance, and it really, you really have to be careful about the multiple comparisons and the power of your analysis to determine this. But even if you could determine the statistical significance of the smoking effect, what good is that? What you really want to know, and what you're going to have to inform your development team or to describe in the drug label, is what is the magnitude of the smoking effect? How much is clearance changed in smokers? And how well do you know that? Is that precisely defined? Is it something that needs to be studied in more detail? And that's something that can't be answered by a simple likelihood ratio test p-value. What you could do instead is to estimate that effect and determine a confidence interval around the smoking effect. Well, the hypothesis testing with these methods should be pursued with caution, and we'll discuss all of this in more detail later. But part of this is because this method is sensitive to assumptions about normality in the residuals, and also to assumptions made in the likelihood approximations. Remember, this is a likelihood ratio test designed to compare true likelihoods, but in a nonlinear mixed effects population model, we're not modeling the true likelihoods. We've made the first order or the first order conditional approximation to that likelihood, and that leads to some bias in this statistic. In fact, it's been shown that FO is not reliable for this sort of comparison, and FOCE and Laplacian interaction methods can be closer. But there still is a possibility that they may be biased too. So it might be more useful to make those inferences by estimation, where you estimate the parameters, construct confidence intervals based on a variety of methods, and make decisions based on point and interval estimates. This is just scratching the surface about some of these topics, and we'll discuss these in more detail as we move forward in the model building examples in this course. So I've left you with some study guide questions at the end of the chapter. These are illustrative of the points that I think are the key points of this material. Take a look at these and make sure that you understand the answers. We can discuss these at the lab sessions, and we can also probably expect that exam topics will be related to some of these points as well.